Hi guys, myself Pranav is here to deliver today's presentation on power transformer part 30. As of continuation, the topic is mainly comprised of bushing technology for power transformers. However, for your convenience, the link of the previous one is given under the description box. Let's start with scheduled inspection every 2 years or 5 years interval for the bushings. Bushings internal insulation is thus to be formed with different class of materials. One, oil impregnated paper. This is the most traditional design, but widely used in high voltage power industry. Number two, resin bonded paper. Oldest technology, but still used for selective applications. Number three, resin impregnated paper. Dry type technology with superior thermal and electrical performance and be used even in UHV application, that is ultra high voltage. Number four, resin impregnated synthetic bushings insulation, mainly used in dry type technology, which involves paperless condenser elements with higher thermal class of insulation, that is class E, 120 degrees centigrade type. Number five, resin impregnated fiberglass, that is dry type technology, which involves paperless condenser elements with higher thermal class of insulation, that is class B insulation, 130 degrees centigrade, and also in class F insulation, 155 degrees centigrade type. Resin impregnated synthetic and resin impregnated fiberglass bushings both are significantly stronger at resisting moisture absorption than paper-based types. So, their inspection is something different. Instead of porcelain, as the other insulation of these two are configured with silicone housing, so these bushings would have the capabilities of higher seismic resistance. Because of hydrophobic property of silicon rubber that prevents flashover related failures. Improved technological evolution of RIS and or RIF bushings over OIP or RIP, that is YP means oil impregnated paper, a resin impregnated paper bushings would thereby to be ensured the distinctive characteristics features as of safety and reliability even under extreme situations like short circuit fault or open circuit conditions occur. Currently, technologies are often offered an extended range of capabilities, including an optional line of smart bushings that use integrated monitoring components. Basically, the main insulation of a condenser graded bushing is thus to be considered as equivalent as of a series of capacitors that separates the conductor from ground. In such a configuration, if the insulation of one of the capacitive screens in the condenser core is somehow damaged, that leads to the failure of other screens and eventually the breakdown of the entire insulation system of its active part, that is condenser core. Failing of capacitive screens means a gradual reduction of series connected capacitors, which causes simultaneous increase in capacitive current. The degree of damage can thus be ascertained by measuring the ultimate variation in capacitance and capacitive current within the condenser core. Based on this principle, an integrated monitoring components are made to evolve for implementing self-monitoring smart bushing technology. Offline testing is thus to be eliminated by incorporating built-in smart measuring circuitry, which is rather to be sealed within the primary core for continuous monitoring of any variation in capacitance current as produced due to failing of capacitive screens within the condenser core. In addition to being a truly maintenance-free technology, smart bushing system has been upgraded with the implementation of an additional special PD sensor, which has made to plug in at the bushing smart measurement terminal for capturing and processing high frequency transient current pulse signals as generated from partial discharge activity inside the power transformer. So we have to put partial discharge sensor for measuring the transient current pulse signals, etc. Technically, it has been established that there is no need to take any sort of hasty decision regarding testing or checking of smart RIS or RIF bushings, as because the design is such that the rate of fault propagation inside the bushings are indeed to be very slow. For 26 kV and below, bushing insulation in system are to be designed by using a solid material such as porcelain, silicon, or resin composite. But for voltages greater than 26 kV, oil impregnated paper bushings are being the most widely used bushing still today, and that has to be designed with layers of conductive materials to distribute voltage stresses and to minimize large voltage gradients. In oil impregnated paper bushing, kraft paper with conductive inserts provides the skeleton to hold the insulating oil so as to make a finely graded capacitive insulation for optimum electrical field distribution. Here, the mineral oil acts primarily as the main insulation as well as serves as a coolant for the bushing. That mineral oil is nothing but transformer oil. The outer shell is typically made of porcelain, but some of the manufacturers are preferred to design with hydrophobic silicone or hermetically sealed composite type of material. High voltage bushings, as installed in equipment such as power transformers, are mostly of oil-filled condenser type, where oil that should provide not only the necessary insulation characteristics but also has to assure their required performance throughout the life of the equipment. It also implies that internal insulation failure is the prime factor for majority of failures of condenser bushings. It is of much importance to note that the voltage gradient between bushing ground flange and bushing's centrally placed HV conductor is of much larger as compared to the voltage gradients inside the transformer or external lines coming into the transformer. Bushing whose lower hub has to extend up to the surface of the transformer tank oil, and its top hub is erected above the tank to a height sufficient to prevent breakdown due to surface leakage. Design of condenser bushing, once developed either in porcelain or epoxy, the physical size of the bushing generally has become reduced. As the bushing is composed of condenser layers, so both radial and axial voltage stress within the bushing configuration have found to be uniformly distributed. It's most important. As the bushing is composed of condenser layers, so both radial and axial voltage stress within the bushing configuration have found to be uniformly distributed. These condenser layers are basically made to form a series of concentric capacitors between the centrally placed conductor and ground. Modern condenser bushings are usually designed for using up to the voltage level of 765 kV use all. For OIP condenser bushing, if its insulating oil thermal expansion chamber that may have been sealed by a nitrogen gas cushion, then a very low moisture content and low bushing power factor may have to be maintained throughout the life of the bushing. Bushing rated 72.5 kV and below have a test tap, while bushings with a rating greater than 72.5 kV have a voltage tap or potential tap. In capacitance graded bushings of all types of equipped with taps, as corresponds to voltage class, for measuring of power factor and capacitance values of the conducting layers. Periodical inspection at intervals 2 to 5 years should have to be carried out for all high voltage bushings. However, periodical inspection must have to include power factor tests for bushings rated above 72.5 kV. Power factor tests can also be carried out for assessing the actual condition of lower voltage class bushings while showing any sign of deterioration. Correlation of capacitive current, dissipation factor, and power factor. Power factor and dissipation factor tests that are ordinarily conducted at site for acceptance test as well as routine testing for condition assessing of the insulation of electrical equipment and apparatus. The basic purpose of conducting these tests is to detect a change of insulating characteristics and thus to track the gradual deterioration of the equipment over its life. Tests are to be considered as non-destructive type since the test voltages should never be exceeded line to neutral voltages of the equipment being tested. Both the tests are referred to be the AC dielectric loss test done under normal operating frequency, that is 50 Hz, for evaluating the status of dielectric loss, capacitance, and AC resistance of the insulation system of the electrical equipment. Power factor, that is cos phi, and dissipation factor tan delta, though these two terms are mathematically be different, but during condition assessment of material insulation, these two have numerically of equivalent values. Now see the diagram. Here V is the applied voltage, I is the total current, IC is the capacitive current, IR is the resistive current, and that resistive current is nothing but the impurities, That current will flow due to some impurities. Phi is the power factor angle, delta is the loss angle or dissipation angle, tan delta is the dissipation factor. Now, see, delta equals to 90 degree minus phi. And that deviation from IC to I mainly due to some impurities, that is for IR resistive current. Basic difference between dissipation factor and power factor is the trigonometry function used to calculate the loss angle delta. Values for both the factors are commonly expressed to decimal values or as a percentage. Now, the vector diagram shows the relationship of applied voltage, resistive current, and capacitive current. If there is no pollution or some defective items or some moistures, then I is in line with IC. But due to some impurities, IR just to deflect I from certain angle, that is delta. Any impurities, if developed in the capacitor zone of the condenser core, then those impurities would therefore to act as resistor. And alternating voltage while applied across an insulating medium having with certain impurities, then the composite unit has to draw a charging current I, which gets divided in two parallel paths, one through the capacitor and the other through the resistor, that is impurity. The capacitive current IC will lead the applied voltage V by 90 degree, and the resistive current IR will be in phase with the applied voltage V. The capacitive current IC is directly proportional to the dielectric constant of the insulating material, area of insulation, and the applied voltage, and inversely proportional to the thickness of the insulation which is under test. Again, I repeat, the capacitive current IC is directly proportional to the dielectric constant of the insulating material, area of the total insulation, the applied voltage, and inversely proportional to the thickness of the insulation which is under test. See the figure. As of figure 121 and 122, A, when AC voltage is applied across an ideal capacitor, capacitive current IC leads the applied voltage V by 90 degree, where IC equals to omega CV. Resistive current IR be in phase with V. See, because of impurities, charging current I leads the voltage phasor V by phi, where phi equals to 90 degree minus delta. From figure 121, IC equals to I cos delta, or IC equals to omega CV, that is omega CV equals to I cos delta. Thus, I equals to omega CV by cos delta. Dielectric loss equals to VI cos phi equals to VI sin delta, because phi is 90 degree minus delta. Omega CV square sin delta divided by cos delta. That means omega CV square tan delta. As because Phasor diagram, tan delta equals to IR by IC. Here, omega equals to 2 pi f, where f is the frequency. Therefore, dielectric loss is directly proportional to frequency, directly proportional to capacitive value C, directly proportional to square of the voltage, directly proportional to tan delta. As the system frequency never changes abruptly, so omega is considered to be constant. For an ideal insulation where there is no impurities, which means no losses, that indicates IR equals to 0. Therefore, the current taken by an ideal insulation is purely a capacitive current leading the voltage by 90 degree. But practically, no insulation is perfect. So, there has a certain amount of loss, and the total current I leads the voltage by a phase angle phi, where phi will be less than 90 degree. Then dielectric loss angle delta equals to 90 degree minus phi. Thus, power factor cos phi equals to sine delta, that equals to IR by I. However, for the insulation of having low power factor, which indicates the loss component IR is very small. So, in that case, IC and I are substantially of the same magnitude. Now, dissipation factor equals to tan delta, that is tan 90 degree minus phi, that equals to cot phi equals to IR by IC. Therefore, dissipation factor equals to cot phi, that is cos phi by sin phi equals to cos phi root over 1 minus cos square phi. Therefore, cos phi is power factor divided by root over 1 minus power factor square. Now, power factor PF is equal to cos phi, that is equal to sin delta, that is tan delta by sec delta equals to tan delta divided by root over 1 plus tan square delta. Therefore, power factor PF equals to dissipation factor divided by root over 1 plus dissipation factor square. Salient points to be noted. As per IEC 60137, the limiting value of tan delta for condenser bushings is 0.007 or 0.7%, and any bushing of beyond that value must be identified as defective one, and the suspected bushing should have to be replaced. It has been exhibited that usual value of tan delta for the newly built condenser bushings is as low as 0.3% to 0.4%. Since the value of tan delta varies with temperature, so for comparison purpose, the tan delta has measured at different temperatures needs to be converted to a common base temperature of 20 degrees centigrade. For conversion of tan delta values measured at different temperatures to the base temperature of 20 degrees centigrade, a correction factor is applied. The chart of the correction factor has to be made according to the behavioral aspects of the insulating material, material structure, the moisture contents, etc. Test of dissipation factor, that is tan delta, for assessing the quality of insulation of the bushing is much more popular in European and Asian countries, including India. But power factor test, cos phi, is rather used to specify the power losses in the insulation part of the bushing. Power factor of an insulation tested under AC voltage and certain conditions as prescribed in the latter slide. The value is to be assessed by the ratio of the power dissipated, that is watts, in the insulation. So the product of the effective voltage and current, volt amperes. Expression as derived from figure 121, tan delta is directly proportional to power factor cos phi, and numerically dissipation factor tan delta is of a very minor difference from the perception of power factor. Actually, power factor test is popular mainly in USA and Canada. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscription would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.